Hey, calculus students, welcome to this extra example video where we're going to look at work problem. This is going to be one of those challenging situations where both factors are varying, both the force and the distance. This time, though, we're not going to be pumping liquids. We're going to be lifting grain from a conical container. So let's see how that plays out. It'll be very similar to a liquid type problem. This time we've got a conical container. As you can see in figure 8 there, it's kind of upside down cone. And we're going to be lifting grain out of this container. This is loose grain, and so it weighs only 40 pounds per cubic foot. So it's a fairly not too dense substance here. Now, a couple of twists here. One is that we're only going to be lifting the top 2 feet of grain, so we're not going to be lifting all of it out. And then another interesting twist is we're lifting the grain 3 feet above the top of the container. Now you might wonder, why would we do that? Lift it higher up than the top. Well, not every container can you lift stuff just right out of it, and you're already there. So what happens here is that there may be a spout coming out of this container, and you got to get it up to the top of the spout. Okay, and the spout is 3 feet. All right, and so we got that extra bit of work there. Now, of course, you could try to compute that part of the work separately. That would be one way to break it down, but we'll just kind of incorporate it all into one computation here. And as we do this, I do want to illustrate some of those key steps of describing your process that are going to be super important to explain that you know how to set up a work computation. Well, of course, the first thing we need here is to establish our coordinate system. And you got choices in doing this, and different choices will have different ramifications. And I thought about, a couple different ways to do this. And I kind of settled on, let's put the y-axis pointing upwards, and let's have the origin of that down here at the bottom of the tank. So x-axis, certainly you need at least one coordinate here. Probably a good idea to have 2 coordinates, have an x coordinate as well. In any case, you got to be clear about what your variables represent, and you're certainly going to have at least one variable involved here. So one way to describe what your variables represent is through putting a coordinate system like this on your picture. Now, this coordinate system, I got to tell you, it's going to lead to some large numbers because if we look at where is the grain that we're going to be lifting, so if 8 is right here, let's see, that means this would be 4, this would be 6. So we got 2, 4, 6, 8. We're going to be looking at the portion of grain starting at 6 and going to 8. So we're going to be integrating from y equals 6 to y equals 8. And that's going to give us some big numbers. But that the counterbalance of that is that our integrand is going to look a lot simpler, I think, doing it this way. So let's try this, and we'll see how that goes. Okay, so let's take a look now at a representative cross section of our grain here. Ultimately, we want to be thinking about a slab. I guess it should really be towards the top here. So I'm going to draw one, right around here somewhere, and we'll say that it is at height y. Okay, so and that's supposed to be circular. Okay, so we got to take a look at the area of this slice. That's going to be A of y. So area of a slice, of course, we want to thicken that up to a volume. We know that the area of the slice is going to be A of y. We can also see that that slice is circular, so we know that it's going to be pi times r of y squared. Okay, now we got to figure out what r of y is. And again, you can't just have this pop out of nowhere into an integral. We got to go through the work to see what that is going to be. Now, let me switch to a different color here, perhaps, to get into that. Let's see. There's my colors. We'll go with purple this time. Okay, so what you can notice here is that our radius is going to be right here. That's going to be the x-coordinate of the point over here, and we can either figure out an equation for the line of that, that line that's at the edge of our cone there, or we can use the fact that we've got some triangles here. Okay, we got similar triangles, and so let's leverage that fact. Okay, let's put the triangles over here. We know at the top, okay, a radius of our very top circle is going to be 4 because its diameter is 8. We know that the height of this entire triangle is going to be 8. But then we also have our cross section here, and we know that that smaller triangle is going to have height y. Again, a definite plus of setting it up this way. And then the other side length of this smaller triangle is going to be x. That's the radius that we want. So, by the way, we could just rewrite this as pi x squared. But again, we're going to be integrating with respect to y here, so that doesn't do us a whole lot of good. We got to figure out what x is. Okay, so setting up the proportions here between the side lengths of these similar triangles, we got x over y equals 4 over 8, and that we can easily rewrite as x equals y over 2. Okay, again, this portion is really simple setting it up this way, so you got to love this part of it. We're going to pay a price for it later, but let's get this in here now. So the area of our slice is pi times y over 2 squared, or if we want to put that square in the numerator and denominator separately, we're going to end up with pi y squared over 4. We just put the 4 out here maybe. Okay, there we go. We got the area of our slice. Again, this is something that you've got to work through. You got to put in each piece here and say, here's the area of my slice. And you'd probably want to say something here like similar triangles, and that's how we set up this proportion. Okay, so now we got the area of our slice. Okay, so if we want to now go to volume of a slab, okay, you want to have that in here too. So that's going to be dV, and dV is going to be pi over 4 y squared. We're thickening it up a little bit. It'll be dy. Now, if we were trying to find the volume of some grain here, of course we'd be set, but that's not what we're doing. We're trying to find work. So we've got to get force here, force and distance involved. Okay, so let me not call that force. Let me call it weight, although of course in effect it is force. So the weight of the slab. Well, now for this, we're going to multiply by the density, which is given to us in the problem there. It is 40 pounds per cubic foot. So the weight of the slab, that is our differential of force. That is going to be 40 times the volume, which again is pi over 4 y squared dy. And so we can simplify that up a little bit and get 10 pi y squared dy. Okay, that's the force, and the other thing that we have here in play is our distance lifted, and remember that now we've got to lift this all the way to the top of that spout, so that's 3 feet beyond the top of the container. I didn't space this out very well here, but let me see if I can erase one of those. Hopefully without messing up too much else. Okay, so we got to get this up to a height of 11. But now it's already starting out at height y. And so the distance that we need to lift that to get it up to 11, since it's already up y is going to be 11 minus y. So the distance, again, you don't need a lot of words here, but you need some words really to say what's going on. The distance to lift the slab at height y is going to be 11 minus y. Okay, and so that means we can get our differential of work. Differential of work is just going to be our differential of force times our distance lifted. Okay, so let's go to a fresh screen so we can get that all put together. Okay, so again, what we figured out here is this is the work to lift slab. That's going to be our differential of work. And so dW is going to be the distance. I think I'll put that first at the moment. 11 minus y. And then our differential of force was 10 pi y squared dy. Let's go back to the previous screen and double check that. Yeah, 10 pi y squared dy. Okay, good. We got it. All right. And so now to get the total work, we just got to integrate, right? So the work is going to be the integral of 11 minus y times 10 pi y squared dy. And now we do need to get our limits of integration in here. Probably a good idea to remember our coordinate system. This was our y-axis. Okay, that's supposed to be a y. Oh my goodness, just getting worse. There we go. Okay, and the stuff that we're lifting, remember, we're not taking all the grain out of the container. We're only going up, you know, we're taking the top 2 feet out, so that's 8 there. And if this was 4 and this is 6, the portion of grain that we're lifting is this portion right here. That goes from 6 to 8. Okay, so that means our integral, our limits of integration are going to be 6 to 8, and voila, we've got our integral set up. Now all we got to do is evaluate it. This should be the easy part. We can pull out our constant factors, 10 and pi. Okay, and if we rewrite what's left a little bit, we can get 11y squared minus y cubed dy. And so again, here is where we're going to pay the price for our particular coordinate system a little bit, because these numbers are going to be pretty big. So we got 10 pi, and when we anti-differentiate, we get 11 over 3 y cubed minus y to the 4th over 4. Okay. And yeah, we got to show this work as well. But remember, it's not just the integral. You want to be showing your differential of work and explain, you know, the distance, the force, and so on, where those different pieces come from and how they fit together. But now we're into computation mode, just integration here. So we put the y in. We're going to get 11. Oh, we got to have our 10 pi out there still. Let's not forget about that. We got the 10 pi. We got the 11 thirds. 8 cubed is 512. You could try to leave this as 8 cubed and so forth, but let's just do it this way. Okay, and then minus. We've got 8 to the 4th, which is 4,096 over 4. That's going to simplify a little bit if we decide to do that. And then we got to subtract what we get when we plug in 6. That's going to be 11 thirds times 6 cubed, which is 216. And running a little tight on space here, but let's subtract 6 to the 4th, which, let's see, that's 1296 over 4. And importantly, we got to remember to subtract all that, so we better put it in parentheses. Okay, so again, different tactics you could take here. You could do some cancellations of numerators and denominators. And actually, you know, that wouldn't be a bad way to go with it. It's not what I'm going to do, but feel free to, you know, pause and take your own approach towards simplifying this down. We do want to get it down to one term if we can. Okay, we still got the 10 pi out front. I'm going to do, let's see, 11 thirds times 512 minus 11 thirds times 216. That's going to give me 11 thirds times 296. Okay, this is the approach I'm going to take with it. Again, certainly not the only one. And then I'm going to do negative 4,096 plus 1,296. That's actually going to leave me with exactly minus 2,800 over 4. Okay, now I'm going to maybe do a little simplification with the fractions. Let's see. So we got no cancellation with that 3 in the denominator there. So I'm going to do 2960 plus 296. That comes from 10 plus 1 over 3. And this second one, we do get some nice cancellation. That's just minus 700. Although I think I'm going to have to get a common denominator for it anyway. 10 pi. Let's see. So we got 32, 3350, I think. Let me see. I think it's going to be 3350. Oh, you know, I forgot I have put, that should be a 6, 296. So 3356 over 3. You kind of wish that would just divide by 3, but it doesn't. Oh, it's 3256. Still doesn't anyway. Let's see. Let's change that to a 32. And I'm going to put that 700 over 3 as well. It'll be 2100. And now we can do the subtraction. So we got 10 pi. And we'll get 1156 over 3. And so that's 11,560 pi over 3. And if you wanted to do a decimal approximation of that, you certainly could. I'm going to keep it exact. And I'm going to put a unit on it. You can think about what the unit should be. Should be foot-pounds. We're in the English system here with force measured in pounds and distances measured in feet. So I'm going to say it will take 11,560 pi over 3 foot-pounds of work. And that's just to lift the top 2 feet of grain out of this conical container. You could do an approximation of that. You could, pretend that this top part was actually a cylinder, and suppose you were lifting all of it 5 feet, and that would certainly give you an overestimate. And I think you'd find that that does come out to be a little bit larger than what we got. So take this as a cylinder. It's a little bit bigger, and let's say you were going to lift it all of this 5 feet up, and you'd get something a little bigger. You get, let's see, did I figure out what that was? Yeah, 6,400 pi. And 6,400 pi is a little bit bigger than this. But this video is long enough already, so we'll leave it for you to do that overestimate, and we'll end it here for this challenging version of a work computation problem, with a couple little extra twists in there as well, with the spout and only lifting part of the grain out. Okay, so I hope you found that informational and helpful, and we'll see you again soon.